Okay, with your upcoming exam, I wanted to go over circle stuff. I wanted to make sure that you know everything about this sheet in terms of how you access it, how you reference it, what it means, where it came from, etc. We have gone through most all of these scenarios. There's some we haven't, like a sphere. We're not really talking about that here. It doesn't have to do with it. But for your upcoming exam, I want to make sure that you understand if this was your cheat sheet and you use these formulas, what do they mean? How do they work? Where you recognize things, because you'll see some problems and you have to make sure that you understand what each of them mean as we go through them. I'm going to skip this one for now. I'll go back to it when after I do these three here. I'm going to start with this one here. Starting with the basic circle, and if this is your center point, which they should have been more obvious about and given you a center point, I'll talk about that later. Here are two radii. Radii are the same distance away in any direction. Doesn't matter where they are. I can draw more radii out here as well. They'll all be the same distance away. So these guys are congruent. Not that it matters here, but it will later. Two radii can form any central angle. This is a central angle. Even this is a central angle out here. It's a lot bigger, but that is one. This central angle's intercepted arc is BC. And the measure of BC is the same as the measure of the central angle. So if this is 100 degrees as a central angle, this is also 100 degrees. That's kind of important to know because there are going to be times where they only give you one and they won't give you the other, right? They're only going to give you, say, this arc, and maybe you have to find an angle out here, and it's based on this angle here, and just a lot of work to be had there. So definitely keeping that in mind. Meanwhile, you'll have something called an inscribed angle. And I'll give another example drawing an inscribed angle here. But an inscribed angle is an angle whose vertex is on the circle itself, not the center like this guy. An inscribed angle is exactly half the measure of a central angle with the same intercepted arcs, like this guy right here. Let's say this central angle is 60 degrees. Then this inscribed angle is 30 degrees. Remember, the intercepted arc is also 60 degrees. And right here, same thing. If this was 100 degrees, any inscribed angle, doesn't matter where I draw it, let's say I draw it here, its measure will be half of that, which is 50. So keeping all that in mind as you work, the inscribed angle, if it's D, equals 1/2 the measure of its intercepted arc or its central angle. If they only give you this, make sure you know that's also half of it. And if I multiply D by 2, I also get the measure of my intercepted arc. 30 times 2 is 60, for instance. Moving on down, two tangents, and here's how I'm going to do this when I've done it like this before, so it shouldn't be unfamiliar. I'm going to go and redraw this segment right here. And I'm going to highlight and group these portions. Okay. So I now have an angle x, and no matter where I move it, this is still x. Okay. Now you also have intercepted arcs here. Well, sort of. You have an arc here that's being touched by this tangent line A, and you have an arc here that's being touched by this tangent line B. So what I'm going to do is draw B green as close to B as possible. I'm going to draw A as red. Close to A as possible, so to speak. I'm actually looking at this formula here. I want to rewrite this over here as well to make sure that you get that this still applies. X equals B minus A over 2. And I'll talk about all the other ones as well as we do this. X equals B minus A over 2. What this means is this angle out here is taking this, the measure of this arc, subtracting the measure of this arc, and dividing by 2. Now, how did this come to be? How did we figure out this formula? Well, it was as follows, because I'm going to do the same thing over here. I take this angle. Let's say I take it and move it inside the circle so that the vertex is somewhere on this circle. Okay? Now, notice what I'm doing here. I want you to pay attention to the area in the intercepted arc between here no matter where I move. Try and recognize that it's the same measure no matter where I move it. Not that you can necessarily tell that instantly, but try and keep your eye focused on it and say, okay, I'm getting the same thing out each time. If we treat this as an inscribed angle, this x, let's say it's an inscribed angle instead. X equals half the measure of its intercepted arc. And the question is, how much is that? Well, we know it's not B, because B is the entire green. Even though there's a B label there, that represents all of what's green. But what represents just the portion inside? The answer is taking all of B and taking out as much as A as there is. So going back here again. Remember, you're trying to find this part right here. There's this intersecting portion A. As I start to move this in, watch how A within the blue starts to shrink. There's less A and less A and less A. As there's less A, there's also less B. How much less B is there? There is A amounts less. Or this amount is being subtracted from this amount to get this amount. And it's hard to say as I'm doing it. I like to point my finger on the screen. It doesn't really work. So here's what I'm going to do. I'm going to take X, move it down here. Right there. I want to find the measure of this intercepted arc. It's going to be half of it, again, just like all of these are. All of these are as well. This is also going to be half the measure. So what I'm going to do is take this A and fix it so that it fits right onto here. And you can tell this is how much I took out. See how the red completely covers the green? If it were perfectly drawn, this red was taken out of this green. All that's left is this little portion right here within the blue. So this measure on the inside is B minus A. I took all of B, took out A. You can tell I took out A. All that's left is B minus A. This angle right here, because it's an inscribed angle, it's half the measure of B minus A. So your angle X, which I never changed, is B minus A over 2, or 1/2 times B minus A. Whichever way you put it is fine with me. I'll do it one more time with this one here, and then I'll ignore it for the third one. Because I want to make sure that you get how you set up those problems as well. Here I have angle X. No matter where I move it, it remains as angle X. So let's go and stick with that. If I move, and here's A. Whenever they're referencing this, they say B minus A over 2. It's the bigger arc minus the smaller arc divided by 2. So I take X, I move it somewhere. I want to move it as an inscribed angle to grab a relationship out of this. And I'm going to move it over here as I do. So you'll see, again, what this means. Let's draw, what I got? I got black. Let's draw B as green again. Let's draw A as red again. And what I'm going to do, when I move over this angle here, A is going to be taken away because it's going to be an inscribed angle. So look at whatever's between the blue segments right here. As I move X in, A starts to disintegrate. B starts to get smaller, but A is going to disappear. You can see that more, 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 and more. And finally, voila, A is gone from within this inscribed angle. Now X is an inscribed angle, and this angle X will be half the measure of its intercepted arc. And the question is, how much is this? The answer is, it's going to be all of B and take away this part. And this part is the same measure as A. If you don't believe me, let's go and take A, rotate it, and fix it right onto here. A is exactly the same measure as the green right there. If I really drew it accurately and drew it to scale, you'd see that it would have fit perfectly there. You take all of B, subtract A, all that you're left with inside here is B minus A. So your intercepted arc is B minus A. Your X angle is half the measure of its intercepted arc, so it's 1/2 of B minus A. It's B minus A over 2. Okay. This one, I'll just do an example problem with it, or a couple different ones. Let's say we need to find this angle X, and we know that this is 100, and this is 30. You're trying to 30 degrees right here. You're trying to solve for X. X equals 100 minus 30 over 2, which is 70 over 2, which is 35. So this angle would be 35 degrees if it intersected here at 30 and intersected here at 100 degrees. That's the basic principle behind it. They might give you a problem similar to that, only maybe they don't give you this value right here. And they give you a center and a central angle. So this is an example of them kind of tricking you up. They might give you this and they might say, okay, this is 100 degrees. And they'll say, this is 35 degrees. and you're trying to solve for A now, you still have to, or well, let's say it was X. Let's say they said solve for X here. This is where I need you to be careful, because X is not this X. This X represents your angle. This guy right here. It doesn't represent the X that you see on the graph or in the diagram. So this X is right here, and try to solve for it. That's for this A. And B is 100, because the central angle is also 100, so is its intercepted arc. So you have to make sure you plug those things in correctly. So we set it up. We say 35 equals 100 minus X over 2. And you're trying to solve for X then. You multiply both sides by 2, subtract 100, or do whatever you get. You'd get X equals 30, because we just did this problem. Okay? Now I'm going to move back on up, because this angle relationship kind of has the same thing as the other ones did. So what I'm going to do is draw 2 bigger segments right here so I don't screw up as I do this. There's one, and there's another. Let's go ahead and put them there. Let's group them together. And I have this big angle right here. Okay, first one I'm going to talk about is solving for angle theta. Okay, that's a Greek symbol. You're going to use it a lot more in later math classes if you still take them. Theta is this measure here. Check this out. We'll take green for t. That's this arc measure right here. Now, theta is not necessarily in the middle of the diagram. It's not at the center point. That's why it's saying, if it's not in the center, how can we figure it out? And R is over here. Whoops. R is right here. What I'm going to do, once again, one more time, just like these examples, is I'm going to take this theta, shift it around. Doesn't matter where I put it, this is still theta. By the way, this is theta as well. These are vertical angles. Vertical angles are congruent. So I'm going to take it, and I'm going to move it. Watch what I do here. Keep shifting it over. R starts to disappear. As R starts to disappear, T starts to grow. Or this arc over here starts to grow. This one starts to disappear. Starts to get less and less. And as this starts to get taken out, this starts to get replaced over there. So I'm going to find out what the measure of this intercepted arc is going to be once I start moving this over. I'll do it one more time slowly. Moving this over, more, and finally, I have created an inscribed angle right here. So theta now resides right here. This is an inscribed angle. Its intercepted arc is formed by these 2 points, so I need to get this whole measure right here. And I need to find out what it is, because whatever it is, theta will be half the measure of it. Okay? So how long is that? Well, it's t plus this amount. And this amount, if you guessed, as r disappeared over there, it reappears over here. So this ends up becoming r, if I did draw it to scale properly. Right there, r gets placed right there. So your entire intercepted arc for this inscribed angle is t plus r, or r plus t. So the intercepted arc is r plus t. The inscribed angle is half that measure, so theta would be equal to taking r and adding t and dividing by 2. So, or I'll put it a different way, 1/2 r plus t. Okay? Now that's when it exists in the middle. I'm not asking you to physically move your angles over. I'm saying this is why this is what it is. This is how it exists, right? So that's what I'm going for when I'm explaining this stuff to you. I'm not saying do this in your problems. I'm making sure that you understand where it comes from, so if you have any doubts about what you're doing, making sure that you get, if it was an inscribed angle, what would happen to its intercepted arc? In this case, the intercepted arc gets smaller. You take all of B, subtract A. Take all of B, subtract A. Here, because it was in the middle, your intercepted arc grows. You take T and add to R. You add to whatever was there. I need to erase this because I'm going to talk about the next thing. We're going to start talking about lengths here. Okay? So as all those go away, now I want to talk about this guy right here, this relationship, A times B equals C times D. As with everything in this semester and with most of geometry, when you do proofs and you talk about things, prove it that way, everything involves similar triangles. Everything. That's just how it comes to be. We're so unfortunate to have that. So what I'm going to do here is I'm going to create 2 triangles, one in blue, right here, connecting these, and one in green. We're getting used to that, blue and green. Okay. Now, we've done a proof, and I'm not going to write the two-column proof, but we've done a simple proof where we said that these two triangles are similar. Not necessarily congruent, but similar. As I said, these two angles are congruent because they're both vertical angles, theta and theta. Now you have inscribed angles, and if you can take a look for 1 second, look at this as a vertex where it's endpoints here and here. So think of this as an inscribed angle, if you can see that right there. Inscribed angle. There's one, and another one, which, by the way, I might want to talk about this over here. All inscribed angles are congruent as long as they have the same endpoints. So check out over here for a second. If I draw another set of things right here and here, that's also congruent to this. D is here, and one more in blue. This is also an inscribed angle because they fall at the same endpoints as vertexes on the circle. All of these are measure angle D. So if this is an inscribed angle with these two endpoints, then this is also an inscribed angle with these two endpoints as well. They share the same endpoints, so these two segments here and here must be congruent because they're both inscribed angles. I could keep going one more time. I could say these are inscribed angles as well with this endpoint, like that, inscribed angle, and then inscribed angle. So these are congruent as well. So you have angle, angle, angle here. You have a proof of similar triangles. You know these two triangles are similar. You have to make sure how they correspond, though. A and D are corresponding parts. If you use side ratios and such, this is where they relate. Same with C and B. It's not going to be A and B and C and D. It's going to be A and D correspond, C and B correspond. So you set up a proportion. You say A over C is equivalent to D over B in the similar triangles. That's where this proportion comes from. You cross multiply A times B equals C times D. 1 second, quick water break. Try and divulge that yourself as well. I should say devour, not divulge. Try and devour that as well. So get a good idea of what that means there. So what we're looking at here in the end, I'll erase all this, are two chords. Okay? Here's a chord going across. It's not necessarily the diameter. There's nothing that says this is the diameter. It's saying it's a chord from circle, portion of circle to portion of circle, portion of circle, portion of circle. They intersect. And it's saying here's the length A that just goes from there to there. Here's B, here's D, here's C. What's the relationship? There is a specific relationship because they have similar triangles here. And it's that A times B equals C times D. So we'll go over an example later with that. Okay, two tangents. We proved this with congruent triangles as well. We had a center point right here, and we said, all right, if we draw another line from here, and then we connect these tangent lines here and here, we've created two triangles. Okay, I could, you see a triangle here, you see a triangle here. And we prove them congruent by doing the following. These are radii. If this is a center, these are radii in your circle. Radii are congruent to one another. So these two segments are congruent. Radii with tangent lines also form right angles. Here's a right angle, here's a right angle. So these guys are congruent to each other as well. Finally, this line is congruent to itself by reflexive property. So you have, this is not, by the way, angle side side. Well, it is angle side side, but that's not a congruency conjecture. But you have two right triangles where you're given congruent hypotenuses and congruent legs right here and right here. So these two triangles are congruent by the HL congruency conjecture. Okay? If these two triangles are congruent, then they have congruent parts that correspond with one another. So therefore, these two segments, R and T, are congruent to each other as well. So R equals T. Whenever you, and the basic thing behind this is whenever you have a point out in space outside your circle, and you draw if you draw the two tangent lines that correspond to that, there and there, remember tangent only touches at one point, then those two segments will always be congruent to each other. Okay? So that's where we got that. So R equals T. These lines are always equal. Okay, these lines are not always equal. These are two secant lines. R and T aren't necessarily congruent. These can be drawn wherever they want to. And Q and S aren't necessarily congruent either. These are also two chords here, just right there. What we did here, and here as well, tangent and secant, is you start to look at relationships here. We proved, once again, that these triangles were they similar. So which two triangles? Let me go and draw them out for you. Let's redo this. Go blue. I'm drawing from here to here. By the way, in my online video, I don't think I gave the best explanation for angle here. I'll give you a quick, better one here. Blue right there, and green right there. Okay, proving that these two triangles are similar. First thing for this proof is you're going to say, well, these two angles are congruent to each other by reflexive property. They share the same angle in both triangles. And then you have inscribed angles here. Let's see, I'll draw it in black. You have an inscribed angle here congruent to an inscribed angle here. You can see they match at same endpoints. Boom, inscribed angle. Boom, inscribed angle. These two angles are congruent. They must be. They share the same endpoints, vertex on the circle. So you have angle, angle. These two triangles are similar. And then you have to match corresponding parts. That's the most difficult part here when you end up doing these two triangles. Here in the green triangle, notice that longest side is R plus Q, that entire thing. And I don't have much room to work with here, so I'm going to do it over here. I'll draw in green right here. I have R plus Q. And here in blue, that longest side over there, you can tell, is T plus S. So those two parts correspond. The other corresponding parts that we know are the short side T in the green. Notice this green right here. The short side is T. So let's pretend like this is the short side, T. And the short side in the blue is R. So here we got a matchup of similar triangles and corresponding parts. So set up a proportion as you do that, and you get, well, T is to R, if I did T over R, as R plus Q is to T plus S. So T is to R as R plus Q is to T plus S. Set up that proportion. Cross multiply, R times R plus Q. Boom, is right there, equals T times T plus S. Boom, right there. I'm going to avoid doing the proof for similar triangles for the next one, but understand again, that's how we got to there. We proved triangles similar, and then we set up proportions, and we said, okay, we cross multiply, you get this statement right here. And here's the most important part about this. And I kind of say it the same way. I say the outside, external, the outside times the whole thing equals the outside times the whole thing. R on the outside of the circle times R plus Q, the entire thing, equals T, this segment on the outside, times T plus S, the entire thing. So when initially you see that and you say that ain't true. There's absolutely no possible way, right? No possible way. Well, we just proved the triangles are similar, and they'd always be similar in these cases for the same reasons I just described below, reflexive property and inscribed angles. Same thing would occur here. You'd get reflexive property and inscribed angles. If I made two triangles here and there, as in this triangle and this triangle, we proved this before in lecture notes. We proved them to be similar. When you do, you set up a proportion, and you cross multiply, and you get to this statement here. And you end up saying R times R plus Q equals T squared. The outside times the whole thing equals the outside times the whole thing. Now the thing is, the whole thing is the same as the outside. That's why it's T times T, which is T squared. Okay, so that's setting up lengths. These are not degrees. These are lengths. Okay. Moving on down here, I'm almost done. This one's kind of peculiar, and it's harder to imagine and look at. But we talked about inscribed angles. We talked about inscribed angles back when, and it said an inscribed angle has two endpoints on the circle, and its vertex is also on the circle. This one's a little different. Here I have a secant line and a tangent line that intersect. I do have my vertex on the circle. I do have a point right here. It's not called an endpoint per se, because it doesn't touch within the circle. But I do have an endpoint here that is on the circle. But this guy, I don't know if it's called an inscribed angle. Obviously, they don't call it an inscribed angle based on this stuff. They're like, oh, this is an inscribed angle. This is a little different. It's like an exception to the rule. It's the extreme most inscribed angle that you can have. But it still counts just like any other inscribed angle that would be drawn with endpoints A and B. So if I draw two more endpoints, like from A to here and here to B, this angle right here is congruent to this angle right here. Just like any other inscribed angle that I draw, much like this one right here, all of these guys are congruent to each other, just like this one here. So when you get a point that ends up being tangent, it goes so extreme that it becomes tangent to your circle, and the other one goes through the other endpoint right there, you still have, I don't know if you call it an inscribed angle, but you still have an angle that's equal to the measure of all the other inscribed angles with those two endpoints. Tougher to recognize. What's even more tough to recognize there is you also have an intercepted arc right here that's BA, just like your other inscribed angles. Actually, I'll bring the green one back. There's your green one right there. Its intercepted arc, as we know, is right here. And obviously, it's half the measure of it. This angle is half the measure of its intercepted arc. This angle right here also has an intercepted arc of AB. Again, not as obvious, but it's the arc that's inside the angle. And this is the one that's inside the angle. So this angle ABC right here still equals half the measure of its intercepted arc BA. Okay, just like any other inscribed angle before it. And again, this one's possibly not an inscribed angle, but making sure you get those. Okay, I'm going to skip spheres. I'll quickly reference area and circumference. Area is the coverage of what's inside the circle. Remember, the circle is that black part. It's the outer rim. This is not the circle. This is the area, which is inside the circle, though. The area is pi times your radius squared. That's a relationship with all circles as you do it. Circumference is taking your radius, multiplying it by 2, which gives you your diameter, by the way. Radius here, diameter here. And there's a constant pi. If you multiply it, it becomes the length of your circle all around it. If you took a measuring tape and put it all around, there's your circumference there. So pi 2r, I put 2 pi r a lot. It doesn't matter. You multiply r by 2, you're left with pi there, or diameter times pi, which is the same thing. There's your circumference. I'll talk about sector area and arc length as well as we do it. Now, there's a difference between arc measure and arc length. I'll do this one first, just because I talked about that. Arc length is how long this is, just like we talked about with circumference. It's a portion of your circle circumference. So this is not going to be in degrees. If this is 100 degrees, and we're looking for the arc length, this is not 100. Excuse me. The arc measure is 100. So when you go back up here, this arc measure is 100 degrees, but that's in degrees. If we're talking about how long it is, arc length, that's a different story. So we're looking down here at these formulas, and you might look at those and go, what the heck is that? We haven't seen that before. We've done arc length, but we haven't seen it like that. Well, you have, and here's how I'm going to expand this. You have a central angle theta. We set up a proportion by doing this. We say theta out of all of 360. If I take this angle, divide it by all of the central angles that add up to 360 here, that's going to be equal to your unknown arc length, right here, x, over the circumference of your entire circle. So which would be 2 pi r, or they put pi 2r. It doesn't matter which way you write it. So when we solve for x, this arc length right here, your unknown, that's going to be equal to, multiply both sides by 2 pi r, x equals 2 pi r, again, as they put, is pi 2r, times theta over 360. So when you see this equation here, that's really what that means. They took this proportion and they cross-multiplied. I wouldn't mind you looking at it either way. I don't mind looking at it this way sometimes too. I like to say, this is the circumference, this is the fraction of your circumference. So if this angle was 120, 120 out of 360 is 1/3, which is why I'm giving this example. If this is 120 degrees, then you're going to take 1/3 of your circumference. So this portion would be 1/3 of your circumference. Here's another third, and here's another third. Okay? That's why I don't mind looking at it that way as well. But we've always looked at it as a proportion. However much this is out of 360 is however this much is out of your circumference. Okay? Sector area is the same thing. And I'm going to use it down here, so pay attention again. Let's say this is the same thing as, like say this is 120 degrees. Or whatever. It's theta right now. We don't know what it is. Set up a proportion. This angle out of 360, central angle out of the entire circle, equals this area out of the area of the entire circle. So this unknown area is just a fraction of the area of your entire circle. X over pi r squared. Cross multiply, well not cross multiply, multiply both sides by pi r squared, you'll get x equals pi r squared times theta over 360, which is where you get this formula right here. Same thing. And again, this is saying, if this was 120 degrees, which is 1/3, you'd be saying, I want to find this black right here, I want to find 1/3 of my area, because this is 1/3 of the entire area. That happens because of this theta right here. That represents what fraction you have. And again, we've looked at it like this. If I get 1/3 right here, I should also get 1/3 right here. Whatever 120 over 360 is, this x, this unknown, over the area of the entire circle should be the same. My fraction over 360 is my fraction of the area of the entire circle. Okay. And final things I want to talk about, just definitions and such. Tangent line is line touches the circle only at one point. Right there. Here's an example of another tangent line. Touch the circle just at one point. Secant lines are lines that touch the circle at 2 points. 1, 2, 1, 2. A line cannot touch a circle at 3 points. It can only touch it at 2, 1, or 0. An example of 0 would be outside there. And that's not something specific. A chord is a segment where its endpoints are on the circle itself. It's like a secant line, only it's cut short. It's just the chord right there. And an arc is just a fraction, or is just a portion of the circumference of your circle. Just like we found arc length, it can be measured in length, or as an arc measure, such as degrees. Arc measure can be 100 degrees, or anything else up there. Okay? Minor arcs, major arcs, and semicircles. An example of a minor arc is like AB right here. And we would write that as AB. Whoa, that's very thick. Let's try that again. AB. Arc AB. It's an arc that's less than 180 degrees, obviously greater than 0, otherwise it's not an arc. I'm going to choose a point over here. I'm going to call it D. And I'm going to draw this arc here. This is an example of a major arc. This major arc is greater than 180 degrees, and I'd have to use 3 letters to define it, ADB. Otherwise, if I just put AB like this, that would mean I'm referring to that one right there. And I want to go in the direction of my major arc. So that'd be ADB. And a semicircle would be, if I put these guys right here, here's the green, my semicircle. This is point E. This semicircle, you can put EB as the semicircle. The only problem with that is EB can go this way or that way. So I'd rather put 3-letter assignments like EDB to be specific with saying I'm going this way, not that way. But this is 180 degrees. Okay? So semicircle is 180 degrees. A couple more things, and I'm actually going to add on. You can write them on the back as we go. A circle. This is the notation for writing circle. You know, just like writing triangle, like triangle ABC. That's a way to write a triangle where ABC are your vertices, your angles. This is circle E right here. It's in this notation. There's a symbol of a circle and an E. That means it's a circle where E is your center point. They'll also write circle E, or they might do a drawing of the circle, and they might label this point E. These are the only 3 ways that you may look at a drawing, to me, or if they say E is at the center, where you know that E is at the center. If they say circle E, that means E is at the center. I want to make sure you know that, because they might just put circle E like this or circle E like this, and they say, what's the measure of this? You have to understand that E is at the center as we do it. Okay, and we talked about radius and diameter. Radius from center to endpoint. Diameter goes through the center. It's twice the measure of radius. I'm going to move on down and give some things that they didn't talk about. One of them I already did talk about, which was if you have a circle, as so, you have a center point, you draw a radius out to it, or out from the center, if it was a good line, and you have a tangent line that goes through and intersects with that radius right there. This measure is 90 degrees. Radius intersects with tangent line at 90 degrees. That's one thing that you really want to know. Here's another thing you'll really want to know. If I have a diameter that goes through the well, obviously it goes through the center, but if I have a diameter, whoa, oh, you can draw arcs. I didn't even know that. Whoa, I could have done that all unit. If I have a diameter that goes through the center, even though it's not an angle by definition, or like, you know, an angle's like this. An angle goes out, you get that. Even though it's not an angle, it's a straight line, it's still a central angle. This diameter still creates a central angle, and I want to make sure that you get that, because here are endpoints. This is the center. This is still a central angle of 180 degrees. If the central angle is 180 degrees, and its intercepted arc, which is a semicircle, by the way, is also 180 degrees. So knowing that information, you might have a problem, and not like an issue, but you might have an actual problem, like a problem to solve, where they say, I mean, they might ask you just what's this angle, but they might give you an angle right here, and you might have to figure out what it is to solve all your other information. And you're like, well, shoot, I don't know. They don't give me anything. Well, they don't give you anything, but they do give you a diameter, and you know that the diameter creates a central angle of 180. This is a central angle. This is an inscribed angle, where its intercepted arc is this guy out here. Well, here's its intercepted arc, which is 180 degrees. This angle, let's call it x. X is half the measure of its intercepted arc and its central angle, so it's 90 degrees. So another good thing to know is that an inscribed angle whose endpoints, let's do this again, an inscribed angle whose endpoints create a diameter is 90 degrees. Okay. All right, that's all I got for you. Hopefully all the circle stuff makes sense. Use this as a cheat sheet as you go. I do bid you best of luck here. I really hope you can recognize how you can use all these different kinds of problems as you do them. And yeah, it's a lot to take in, but if you have these rules and you understand them in your own way, I think that would be very fortunate for you.